Hey, everybody, this is Mr. Conklin. I'm talking and broadcasting, so to speak, from my home office, as it were. Read that. This is down in my basement with the webcam on. Just wanted to give a couple of explanations as to where some of the formulas from sixth grade advanced math come from, especially with the arithmetic and geometric sequences and series. Just to start, an arithmetic sequence, arithmetic, let me grab my glasses here so I can see a little bit more properly. An arithmetic sequence, it looks like the word arithmetic, but this is meant as an adverb. Let me hit zoom here just real fast so it gets a little sharper there. Okay. An arithmetic sequence, and by sequence, I mean any list of numbers that is separated by commas. So just a plain old list. So for example, 2, 4, 6, 8, dot, dot, dot. This is just a list of any numbers at all separated by commas. And this thing is wobbling. Sorry. Let me see if I can move this thing around a little bit. That should be a little bit better. It's usually follows some sort of pattern. It doesn't absolutely have to, but a sequence can be any list of numbers at all. But the ones that we pay attention to, let me focus this one more time, are going to follow some sort of predictable pattern. And there were two main types of sequences. There's something called an arithmetic sequence and a geometric sequence. Let me just write that in. Geometric sequence. An arithmetic sequence, I'm sorry, I'm running out of room here. An arithmetic sequence is a sequence that is generated by, and generated just means produced by, generated by, I'm writing on a TV tray here, so I apologize if it's, I think I can get better focus than that. Okay. I apologize if this is a little bit on the messy side, so that the whole tray wobbles. The sequence generated by adding the same number repeatedly. This list up here, 2, 4, 6, 8, that is an arithmetic sequence because they're adding the number 2 over and over and over and over. They're by adding the same number repeatedly, and that number in question is called D, which is short for the common difference. Now, in math, a difference is the answer to a subtraction problem. So if you want to find out how far apart these numbers are, you subtract any pair of them. 4 minus 2 is 2, 6 minus 4 is 2, 8 minus 6 is 2. They all have the same difference between them. That's what we call a common difference. So we call that D for common difference. So any arithmetic sequence, if somebody says this is an arithmetic sequence, my response to them is, okay, prove it. Give me the value of D. Here's another quick example. Kind of running, I may have to do the geometric down here. But if I do 3, 8, 13, 18, blah, 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 and they say, is this an arithmetic sequence? I will say, yes, it is arithmetic. Arithmetic. And then the proof is, can you give me the value of D? Yes, the value of D is 5 because they're adding 5 over and over and over again. Does that make sense? So an arithmetic sequence is a list of numbers that's in a pattern by adding the same common number repeatedly, and we call that the common difference. Geometric sequence is a sequence that's a little bit different. It's still a list of numbers, but it's generated, I hope you don't mind me abbreviating there, by multiplying. And sorry, this thing is going in and out of focus. The reason is I've got a this sort of TV tray thing is a little bendy flexy, so I hope it's not too blurry. So it's generated by multiplying the same number repeatedly. And that specific number we call R for the common ratio. Now, a ratio, another word for ratio is fraction, which is a division problem in condensed form. So like 3/5 is really 3 divided by 5. So anytime you're multiplying by something, let me give you a quick example of what that means. An example of a geometric sequence might be 3, 6, 12, 24, 48, and so on. If somebody says, is this geometric? Yes, it is. Why is that geometric? Or prove it. Does it have a value of R? Are they multiplying by the same number over and over and over? The answer is yes, they're multiplying by 2. So R is equal to 2. That would prove that it's geometric. Does that make sense? So there's what we have so far. There's the definition of an arithmetic sequence and a geometric sequence. Arithmetic is when you add the same number over and over to make the list. And geometric is when you multiply the same number over and over and over to make the same list. And again, a sequence is a list of numbers separated by commas. Now, there is such a thing. There's a sequence, which we've already covered, versus a series. A series is a list of numbers that is separated by addition signs. In other words, that's a big fancy way of saying a series is a sum. A sum is the answer to an addition problem. For example, the same list we have over here for an arithmetic sequence, I can turn it into a series by doing 3 plus 8 plus 13 plus 18 plus blah, 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 blah. This has become a series. It's still an arithmetic series because D is equal to 5. You still generate it by adding the same number over and over and over. But instead of just listing numbers, sorry, it's a little crooked here, we're actually adding them, and you can actually get a sum, a total for that. Let's see if I can focus this one more time. Maybe I can get this thing to. Okay. Well, if it goes too far off kilter, I'll try and adjust it a little later on. So hopefully that's kind of straight. Two differences here: sequence versus series. A sequence is a list of numbers with commas, just listing the numbers themselves. And a series is when you actually add them up. And arithmetic versus geometric, arithmetic is a list generated by adding the same number over and over. And geometric is generated by multiplying the same number over and over and over. Now, question comes up, if it's a predictable pattern, is it possible to predict future numbers? Well, just as a quick example, let's take I'll start with an arithmetic sequence. I'll do the one we had up on top, 3, 8, 13, 18. I'll go it out one more time, 23, and blah, 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 blah. As kind of a shorthand, we label each of these. These are terms. This is the first term in the sequence, the second term, and we call them A1, A2, A3, A4, A5. So A1 is code for the first term. It's term 1, or the first term. A2 is the second term, A3 is the third term, and so on, so on. Eventually, the book may ask for what we call a They sometimes do a sub 1 because sub means below. This is a sub 1, a sub 2. They might ask for a sub n. They said the nth term, if they say, can you predict the 50th term? Maybe. We'll find out in a minute. But if it's a predictable pattern, the answer should be yes. How do you do it? We'll find out in a second. But again, this would be the, if you want to call it sounds a little funny, but the nth term. So in other words, any term you want, you could fill in n equals 100 to get the 100th term, and so on. So how do you get the nth term of an arithmetic sequence? First of all, this is arithmetic. And you prove it by giving the value of d, which in this case is 5. This is the common difference. So how do you get a predictable number? Well, we do know that every time you want to get to the next term, you add 5. Now, like over here, I'll just demo this. Every single jump here is adding 5. I do want to point out something a little bit weird, though, and this is going to help us on our next formula. The number of terms, like it keeps going, but there are 5 terms displayed here. Look how many jumps there are between. Not 5, there are 4. So the number of times you added 5 is not 5 times, it's 4. The number of terms is always 1 more than the number of jumps between them. Or flip it around, the number of jumps between them is always 1 less than the number of terms. Does that make sense? So if there are 10 terms, there would be 9 jumps in between them. The reason we want to know about that is because, do I have this thing? Oh, I see, this is exposure. Hang on a second. Yeah, that's a little better. Hopefully this thing will zoom. I set this to automatic zoom. No, actually that's just zooming in whenever I put my hand in. I'm sorry. I'll just try and I hope this is legible. It doesn't look incredibly clear on my screen, but I hope that clears up soon. Anyway, just to refresh, if you have a certain number of terms, the number of jumps between them is going to be 1 less than that. So how do you predict the next term? Well, it turns out you start with, if you want to get the nth term, you start with the first term, which we call A1. Does that make sense? Then you're going to add something else. We have to add 5 a certain number of times. So I'm going to, well, in this case, D. In this case, it's 5. So you take A1, which is the starting term, and then you add whatever the common difference is over and over and over. So we're going to add D, but the question is how many times? So this is going to be the size of one jump, quote unquote. And by jump, I mean how far it is between any two pairs next to each other, terms next to each other. So, and A1 is the first term. That's where you start counting from. Okay, so how many jumps do we need? Well, if you're going out to the 5th term, you have 4 jumps. Remember, it's 1 less. If you go 10 terms, it's going to be 9 jumps. Well, what if you have n terms? Then it makes sense that it's going to be 1 less than that, or n minus 1. We have just found the formula to generate the nth term of an arithmetic sequence. So if I want to get the 100th term, just for an example, let's just say I want the 100th term of this particular string. It says start with the starting number, which makes sense. So it's going to be 3, plus then the size of your jump. Oh, yes, and this represents the number of jumps, which is always 1 less than the number of terms. So how big a jump is, and then how many jumps you actually do. So let's hear, you start with 3, and you're going to jump a certain number of times. Well, how big is each jump? You're adding 5 each time. How many jumps are we going to do? Well, I want to go to the 100th term. So they're going to be 99 jumps, 100 minus 1. Now you just calculate this out. This is, in the parentheses, is 99. 99 times 5 is 495 plus, feel free to use calculator or paper on the off to the side if you can't do that in your head. And this would add up to 498, and I can guarantee you that's the 100th term. Does that make sense? So that's the principle behind the first formula that we ever learned. How do we get any given term in an arithmetic sequence? Use this formula. This is one you have to memorize, but this is where it comes from. Again, the any given term, start at the first term, and then jump this many times, and this is how big each jump is. So that's where the formula comes from. Okay. Next, I'd like to, oh, that's some scribbling left over from a previous assignment. I would like to try geometric. And let's try the one we did before. It was 3, 6, 12, 24, 48, blah, blah, blah. And again, we're calling this A1, A2, A3. This is the first term, second term, third term, and so on. And eventually you're going to ask for the nth term. First of all, let's make doubly sure this is geometric. Turns out, yes, it is. It is geometric because they're multiplying by the same number over and over and over again. In this case, 2. You would say that R equals 2. There's your proof that it's geometric. How do you get like the 10th term or the 20th term, though? Well, it turns out if you want to get a sub n, again, this is not for arithmetic. This is going to be a different formula because it's for a geometric term. How do you get the nth term of a geometric sequence? Well, you still start with a1, the very first thing. But instead of adding over and over, we don't put an addition sign here. We put multiply. We're going to multiply it to something. Now, what are you multiplying over and over and over again? It's whatever your special number is, the common ratio. In this case, it'll be 2. But the question is, how many times do you multiply? So let's say if this is a5, notice this is times 2, times 2. I'm using a little dot for times. Times 2, times 2. And the same funny thing happens. If you have 5 terms, there are 4 jumps in between them. If there are 10 terms, there are 9 jumps in between them. And if there are n terms, there's going to be n minus 1 jumps. Now, what's the short way of saying times 2, times 2, times 2, times 2, times 2 a bunch of times? Let's say you have 2 times 2 times 2 times 2 times 2. There is a short way to write that. It's using an exponent. It's like 2 to the 5th power. So if I'm multiplying by 2 lots and lots of times, it's going to be 2 to some power. In this case, it's going to be r is 2. So 2 to what power, though? Well, if I have n terms, I'm not going to raise it to the nth power. It's going to be 1 less than that. This is the formula for finding the nth term of a geometric sequence. So in this particular case, let's just say I want to find a 10. I don't want to do 100 because when you're multiplying, this gets huge really, really quickly. We're going to start with the first term, which is 3. And then you can put a times here, but parentheses shows multiplication pretty well. 3 times what? Well, r is 2. And in this case, remember, this is a value of n. This is how many terms you want to try. 3 times 2 to the, I'm not going to raise it to the 10th. I'm going to raise it to the 10 minus 1. Because if there are 10 terms, there are going to be 9 jumps, 9 multiplication jumps. So what this is 2 to the 9th power, which I looked up earlier. 3 times 512. And 3 times 512, that's 1536. So that is the 10th term of this geometric sequence. So if you went out to A10, it'd be 1536. Does that make sense? Okay. There's only one other, there are 2 other formulas I'd like to cover. The third formula is actually kind of clever. That's called an arithmetic. So we're going back to the addition one. Arithmetic series. Now remember, series means you're adding the terms, not just listing them with commas. How do you add up a bunch of terms? And is there a shortcut to do it? I mean, you could always just list them all out and then add them up by hand, which takes a long time, but it's better than nothing. But the question is, suppose you have For example, what was the one I used last time? Hang on a second. Um, I had 3, 8, 13, 18. I'll use that exact same one. Sorry about that, flipping the page all over. So 3, 8, 13, 18, 23, then blah, 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 forever. If I wanted to get a series, I'm going to use, instead of a sub n, which is the term. Oh, by the way, I think the textbook sometimes uses T1, T2, T3, which I can understand. It's term one, term two, term three. It's just A1, A2, A3 was in older usage before this. I'm not quite sure why. I think it has something to do with the fact that these were first played with in a country that wasn't speaking English. But A is the sort of classical way to do it. But using T1, T2, T3, that's totally fine. I think the textbook actually does use T1, T2, T3. It's just A1, A2, A3 is sort of more canonical. Anyway, well, back to here. Instead of saying, this is A1, A2, A3, to get a series, you're going to get capital S sub n, which is what we call the nth sum. Another way of saying the sum of the first n terms. So in other words, S10 would be, sorry, it's crooked. S10 would be the sum of adding up the first 10 terms. You have a pretty big answer probably, but it's whatever that is. S10 would be adding up the first 10 terms. S100 would be adding up the first 100 terms, and so on. So S for series, also S for sum. So it's pretty easy to remember on that. So how do you add this? Well, it turns out there's a little bit of a story, and I told this in class, but for people watching at home, this is kind of neat. It's a true story. Whoops, misspelling the poor guy's name. I think it even spelled with a K. Carl Friedrich Gauss. Carl Friedrich Gauss was an extremely famous mathematician, I think back in the 1700s-ish. But he, the story goes, and there's some reason to believe that this is pretty accurate. They might have embellished a little bit, but he was the center of the story. He was a child, and the story says he was 8 years old when this story came about. He was at school, and they had a substitute teacher who was a little on the lazy side and decided to give the kid some busy work so that he could kick back on his desk and daydream for a half hour or so. He gave the kids, and the kids had there were these little slates, these sort of handheld chalkboards. And they weren't very big. It was about 1 foot by 8 inches or so. Is not very big. So all the kids had a slate, which is a tiny chalkboard, and a rag and a piece of chalk. The rag was to wipe it clean, and the chalk was to write, and the slate, not much room. The teacher gave all the students in the room the assignment of adding up the numbers from 1 to 100. I'm not going to write them all out because it'll take forever. 98, 99, 100. Now, if you can imagine doing this by hand, they would write 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, and you've run out of room. So you have to quickly remember your 15, erase, 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 put 15 up here, and then remember where you left off, plus 6, plus 7, plus 8. It gets worse and worse and worse as you go on. And it's going to take a long time. However, the story goes, the teacher was, hopefully not too smugly, but walking back to his desk. When he was startled by a clack on his desk, he turned around and he found that little Carl Gauss had dropped his slate onto the teacher's desk with the correct answer in less than 10 seconds. And he did go on to become one of the most famous mathematicians in the world. But let me show you how he did it. Almost everybody tries to do 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus, and it gets slower and slower and slower and slower. Watch this. Carl did not add them in order. He said, what's 1 plus 100? the first and the last. Turns out it's 101. But here's where the clever part comes in. Now we did the next pair in. What's 2 plus 99? It's 101. What's 3 plus 98? 101. What's 4 plus 97? 101. You get the same answer every single time. When you take the first and last number and then the first and last remaining number, the first and last, so on, you always get the same answer. And he thought, okay, if all of these pairs are 101, how many pairs are there? Well, if there's 100 numbers and pairs are 2, there are 50 pairs. So we're going to get 101 50 times. Multiply this out and you get 1,000 or 5,050. And that was the correct answer. Isn't that amazing? Anyway, so bravo, Carl Gauss. Here's what you do. If you have an arithmetic sequence, like, well, let's take the 3 plus 8 plus 13 plus 18 plus blah, 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 all the way up to a sub n. I mean, I have no idea what this would be. All I know is that this is arithmetic. D is equal to 5. A1 is equal to 3. That's all I know. Now, suppose we knew what a sub n was. Suppose we knew. I'll show you how we can know in a moment. But let's put this off just for a second. Look up here. What Carl Gauss said is if you want the nth sum, so the sum of the first whatever, you take the first term plus the last term. And you don't have to, that's going to be the same answer over and over and over. But how many times? Remember, n is the number of terms. And he said we're going to do that the number of pairs. So it's half as many. This is Carl Gauss's formula. And that's it's often written with n over 2 in the front because it looks a little better. So n over 2 parentheses first term plus last term. That is guaranteed to get the right answer. And it's very clever. And it's invented by an 8-year-old boy, which is really mind-blowing. But let's try it with the 1 through 100. So S100, let me scoot this up so you can actually see what I'm doing. S100 would be equal to the number of term, or the number is 100, cut in half. So this is the number of pairs. And then the first term in this case would be 1. The last term would be 100. And then just multiply that by 50. And you're done. So the catch is you have to know how many terms there are. You have to know the first term and you have to know the last term. Once you do that, ta-da, all done. The question is, how do you find, what if you don't have the 100th term? Let's say we do this this is the one I was doing before, 3, 8, 13, 18, 23, and then blah, blah, blah. And suppose I want to add up the first 100 terms of this monster. Well, I have a problem here because I don't know what this is. What is A100? Well, let's set up what we do know. We do know that S sub n, according to Carl Gauss, is n over 2. That's the number of terms divided by 2. That's the number of pairs. How many pairs are going to add up? And then it's the first term plus the last term. Okay, so we can do a little bit. We do know that n is 100. So that's 100 terms. Divide by 2. That'll be 50 pairs. And I do know the first term. It's 3. Plus something. Now we're stuck here. I mean, I can make this 50. Yeah, well, great. But I don't know what this is, so I can't finish the problem yet. But if you remember from about a few minutes ago, I know how to find this. And so do you. A sub n for an arithmetic sequence is A1 plus D, which is how big the jump is, times n minus 1. So in this case, it's 3 plus We do know this is arithmetic because d is equal to 5. 5 goes here. And then his how many terms? 100 minus 1. This will give us the missing term we need. I'll show you a little trick here too. Normally I do parentheses first, so it'll be 5 times 99. There is another way to do it. You can distribute. And it turns out that's actually kind of a lot easier to do in your head. Everybody see what I just did? I distributed 5 times 100 and 5 times -1. So it's 500 minus 5. So 500 minus 5 is 495 plus 3, 498. Now, we knew that from the previous page, but 498. So this answer is going to be 50 times 498 plus 3 is 501. So let's do that. 501 times 50. So multiplying by 0, just going to get a bunch of zeros. This is going to get 5, 0, 2, 5, 2, 5, 0, 5, 0. That is the sum of the first 100 terms of this sequence. Isn't that amazing? And we have Carl Gauss to thank for that. Utterly incredible. The geometric ones, I kind of have to put on faith here. The geometric one, there is a proof for it, but it's really kind of obnoxious and it takes a lot of advanced math, sort of on the pre-calc level to understand the proof. So this is one you just have to memorize. So if you have Sn for geometric, there's good news and bad news. The good news is the formula has a certain pattern which makes it easier to memorize. It starts with A1, and then we're going to multiply because it's geometric, but it's going to be a fraction. It's 1 minus r to the n over 1 minus r. Okay, so it's starting with A1, and then you notice the top and bottom are almost identical. It's 1 minus r, 1 minus r. The only difference is that the r on top is raised to the nth power. This you'll just need to memorize. So if you have to memorize just by raw brute force, focus on this one. All the other ones you can kind of figure out where they came from. It is easier if you memorize them just plain old, but if you get stuck, you can always derive them if you will. Now there is one other. It's called an infinite sum. In other words, if you have an infinite number of terms and you add them up, what would happen? Now, most people would say, well, if you have an infinite number of terms, it's going to be infinity. It's going to blow up. There's no way to get a real finite answer. As it turns out, that's actually not always true. Sometimes we do get an interesting answer. Let me give an example. There's a relatively easy one. That actually does give you a nice, easy answer. If it goes to infinity, the answer is still 0. Here's a weird one. See what I'm doing? 1 plus -1 cancels. 1 plus -1 cancels. 1 plus -1 cancels. So it kind of depends on if they're an odd number of terms or an even number of terms. This one actually doesn't have an answer because we don't know. Infinity, is it odd or even? I don't know. And nobody knows. So you can't get an answer. But I just wanted to demonstrate that it is possible to get some unexpected answers. And somebody discovered a long time ago 1/2 plus 1/4 plus 1/8 plus 1/16 plus etc. You notice how these are just cutting in half. Half of a half is a fourth. Half of a fourth is an eighth. What happens? Could this go forever? Would it be infinity if I get an answer? Well, let's check it out. 1/2, let's just draw it like a pie or something. Half of a pie would be this, right? Now let's add on a quarter to that. So it's 3/4 so far. Now add on an eighth, which is half of the remaining space. Now add a 16th, which is half of the remaining space. Oops, I have to draw this correctly. And then add 1/32, half of that. Do you see what's going to happen? It's going to fill in more and more and more and more and more, but never actually close up as long as you keep adding. But what if you actually went forever? you're not going to get an infinite number of pi's. Turns out the answer is 1. You're going to get 1 complete pi. If you go forever, you'll finally fill in the rest of this thing. It's weird. It's kind of hard to picture in your head, but it does prove that there is such a thing as an infinite series that has a nice total, that has a finite total. There are actually 2 conditions when that happens. They don't always, because if you try to do 1 plus 1 plus 1 plus 1, it's a nice, easy thing to add. But if you go to infinity, that's going to go to infinity. It's going to blow up. So it doesn't work. There are only 2 conditions where an infinite sum will actually work. First is it has to be geometric. It cannot be arithmetic. Second, R has to be between -1 and 1. In other words, it has to be a fraction, like 1/2 or 1/3 or 2/3. It can't be 1 or bigger, and it can't be -1 or smaller, because that would mess up the sum. These are the 2 conditions by which an infinite sum would exist at all. And in this case, you'll notice this is geometric. They're multiplying by the same thing over and over. And you'll notice what they're multiplying by. They're multiplying by 1/2. So first of all, that proves it's geometric. Times 1/2, times 1/2, times 1/2, times 1/2. They're generating the list by multiplying the same number repeatedly. And if you notice, R 1/2 is between -1 and 1. So it's a good value of R. So how do you get an infinite sum? It's this. It looks almost the same as the one above. A1 parentheses 1 over 1 minus R. You notice the minus R to the n just disappeared. And there's actually a reason for this. As n goes to infinity, what happens to R to the nth power? Well, if R is a fraction, if it's a small fraction, for like 1/2, to a really, really big power, well, what's 1/2 times 1/2 times 1/2 times 1/2? The question is it getting bigger or smaller? Well, here it's 1/4, here's 1/8, here's 1/16. Look at these numbers. They're getting smaller. A quarter is smaller than a half. An eighth is smaller than a quarter. So 1/2 to a really big power is a really, really small number. So what do you think would happen if you raised 1/2 to the infinite power? It would get infinitely small or turn into 0. I mean, you can't actually get to infinity, but basically as this goes toward infinity, this goes towards 0. So this R to the n thing gets so small, it gets smaller, 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 disappears. Does that make sense? So that's where this formula comes from. That is the formula for an infinite sum. So this one, again, I'm sorry I didn't give you a derivation of where the formula came from, but it is very complicated. But I did give you at least an explanation for where the infinite sum comes from. It's a geometric, it has to be. So it's based on the geometric sequence or series. But as the power of R gets enormous, which and going to infinity it would, this just disappears. It's basically 1 minus 0. So it's just 1. And everything else stays the same. And it's quite easy to compute. Let's try it. The formula, so S infinity is equal to A1, which is it's 1/2, the first term. And then we multiply it to 1 over 1 minus, what are they multiplying by? Now, this is kind of funny because the first term and the value of R are identical. That's coincidence. I could have started with any number at all. So 1 minus 1/2. What's 1 minus 1/2? What's 1/2? How do you divide by a fraction? Well, there's a trick in math to divide by a fraction. You multiply by the reciprocal. So, well, the ones cancel, sort of. And then 1/2 times 2 is 1, which is exactly what we thought it was. Anyway, that is it. So, sorry, I was pointing at the wrong thing. This is the value of 1, which agreed perfectly with what our pi diagram is doing. And that is it. That's where the formulas come from. Hopefully that was helpful. So let me know. If you have any other questions, email me. Otherwise, God bless your efforts and talk to you later.